because it is under what? Compression. Likewise, the delta L is in what? Minus. Okay, the negative sign declare is under what? Compression. Okay, the negative declare there is going through compression. Now, without buckling, or when the structure did not fail by buckling, okay, when the structure did not fail by buckling, the deformation pattern is parallel to the what? Centroid, right? So I'm going to draw in light green. So when the load is applied, the structure deform, right? Slowly deform, slowly deform, slowly deform, and it's parallel to the centroid. Okay. So this is very different. Okay. So when or during buckling analysis, the deformation pattern is different from just under normal axial or normal compression axial loading, okay, without buckling. So what is the difference? So I'm going to sketch for you now the difference. Okay, what is the difference? So this is the so what we have now is we have okay, and then I'm going to draw okay, and over here we have a pin. And then we have a block down here. This block can only slide up and down. And then we have a load. We have a load now acting here in P. Okay. So I want you all to get used to this. So I'll call this our point A, our point B. So point A is pin, and point B is also pin. Okay. So the difference, so if I were to draw our transformation, X and Y, and this is our rotation about Z. Okay. So at point A is pin, at point B is pin. And because it's pin, okay, I want you all to start realizing this. the moment at point B is equal to 0, right? It's pin. And the moment at point A is also equal to what? Also equal to 0. Again, this is because it is pin, okay, for that reason. Okay. So now once we start having a load that has been applied now, okay, and I'm going to sketch out our centroid. Okay, so this is again our centroid. Okay, so the next sketch I'm going to do for you, or before I do for you any sketch, if you look at point B, right, the one of the condition at B is x is equal to 0 and y is also equal to 0, right? But the moment is also equal to 0. The moment at A is equal to 0. Now, if we look at A, right, x is equal to 0, y is not equal to 0 because you have what? You have rollers down here. Yes or no? Let me zoom in so I can maybe have to draw the rollers better. Okay, so we have rollers. Rollers means it can go up and down. Okay, it cannot go what? Left and right. Okay, so the next thing I'm going to do is I'm going to sketch for you, okay, the deformation pattern during buckling. Okay, so the next sketch. So now if P increases, I'm going to sketch for you deformation pattern during buckling. Okay, so the green line, I'm going to take the green line again. I'm going to sketch the green line. So I'm going to have call this our point. Okay, and then I'm going to have another point down here. Before I go on, I need to make some changes. Okay, can you all change this diagram over here? That this is your y and this is your x, because I'm going to write up a mathematical transformation. So if that's the case, y is equal to 0 over here, x is not equal to 0 because it can move up and down. Okay. So the next thing I'm going to draw now, okay, is I'm going to draw an axis now. Okay, so this is our y-axis. And then we are going to draw, oh, I'm off. This is our x-axis. Okay, and over here. And we have a certain length over here. And this thing is our L0. Okay, so basically, if this is 0, this location is our L0. So the next, I will draw the centroid, I will draw the deformation pattern. So I'm going to sketch the deformation pattern during buckling. Okay. Okay. So this is our deformation pattern during buckling. Okay. And you can see it's very different when there's no buckling. When there's no buckling, the deformation pattern is parallel to the what? Parallel to the centroid. Now, the deformation pattern is a curve. Okay. So in this context, we have to now, it's not we, but the theory of buckling states, okay, that now we have to mathematically describe how the structure is deflecting or bending. Okay. Okay. So anything that is math, we need to have boundary condition. Okay. And unfortunately. So we are going to have our boundary condition number 1. Okay. Which over here it states that when x is equal to 0, y is also equal to 0. Okay. So boundary condition 1 reflects to this point over here. And then we have boundary condition number 2. Okay, we have boundary condition number 2, where x now is equal to y naught, y is equal to 0. So from here, we are going to pick a point. Okay, we're going to pick a point. And this point we're going to pick is somewhere down here. And this is our point Q. And at our point Q, it has a certain distance down. And this is our x. And with that x, it has a certain distance y. Okay. So the y over here describe our deflection. Oh, sorry. Should not write over the text. Okay, so the y over here is the deflection. Okay. Now we are so this is the deformation pattern. Now, if we are going to deal in terms of forces, what is going to happen at point Q? Okay, so I'm going to copy. No, I don't need to copy. I'm going to now. We are going to declare at this point, right? This is our point A. Did I call it point A? Yes, I did. Okay. And then at point A, I'm going to draw the green line, which is the original position when the force is applied. Now remember, point A cannot move anywhere, okay? Because we are restricting it to move in the y direction. It can move in the x, okay? So originally, we know that over here, we have a P, okay? And then because of buckling, we are having a deformation. And now at this point over here, okay, or at this point over here, this is now our point Q. And we are aware that at point Q, right, we have a certain distance from here to here, which corresponds to our Y. So at point Q, right, at point Q, we have a load to counter the P. This is our copper, P prime. And then the P, right, will be inducing the P will be in because of at point Q. Let's focus at point Q, okay? The P will induce a moment coming in this direction. So this is moment at point A. Okay. So by applying Newton's